Welcome to the second tutorial of DLPGEN. In this tutorial, I'm going to try to show you how you can start preparing the input files for DLPGEN from scratch. And for this, I decided to make you a small example for phenol. In this case, the first thing I need to do is to create a folder to put all my data and then start preparing the files. First thing I'm going to do is I'm going to desktop, okay, and I'm going to create a folder here for my files. So I create a folder called phenol, okay, and I'm going inside of it. Now, DLPGEN creates a lot of temporary files. So to avoid or to be easy to understand what are the output files from DLPGEN that will be later on used in the AMD simulation programs, I normally create a folder called mols, which will contain all the temporary files for DLPGEN. Now, the next thing I want to do is to create a gen file for DLPGEN. And to do this, I'm going to start by creating a PDB file containing the information about the phenol. Normally, I like to use Gauss view, and I'm just going to start by running Gauss view. And in here, I'm going to draw the phenol molecule and then save it. I like to use Gauss view because it's very handy and it has a lot of interesting features that can be used for this to draw a molecule. For example, in this case, I just draw the phenol molecule, and the hydroxyl group is perpendicular to the aromatic ring plane. So the first thing that I want to do is to put it in the right position and flip it or put it in plane. So I'm going to use this torsion angle option, change this for 0, and now everything is in plane. Next thing I'm going to do is to save the file. I'm going to save it and I want to save it as a PDB file. And now I want to, in this case I already in the mols folder, so I'm just going to call this folder or this file phenol.pdb, and now I should have a PDB file inside my mols. Oh, sorry. I'm changing to the mols, and now I have the phenol here. And as you see, this is just a normal PDB file containing the information about the atoms and the atomic coordinates of the molecule. So the next thing I need to do is to prepare a PCF file for my program. And for that, I'm going outside of the mols folder, coming to the root folder for phenol, and I'm going to create a PCF file using nano. And to create it, I'm going to use as a starting point the examples in the manual of DLPGEN. And I'm going to my webpage, download the manual, and now I'm going to look for a section where it describes the PCF file structure, and here it is. So I'm going to copy what we have here now, and I will start then trying to fill this with the new information. So first thing is that this is phenol example. The temporary file's location is mols, as it is here, described here. There is just one small thing. I normally like to put some space between the instruction and the folder name. Now, in my case, I'm going to have only one molecule, which is phenol. And here I need to say that it's phenol, my molecule. And then I will want to create a simulation box containing 200 molecules of phenol. This is not needed. And then we have the simulation box's dimensions. So in this case, I will put 10. And of course, the alpha, beta, and gamma is 90 degrees. These values can be also used to get triclinic or monoclinic simulation boxes if you want. Number of cells repetition. These options are necessary if you want to stack several unit cells of a crystal structure. In this case, you can just remove it, or you can simply set as 1 in this case, because I don't want to stack several boxes. And the last entry here is the force field file, which in this case I will create one specifically for my program, for this example, and it will be placed in the moles folder. Normally, I always use the same library every time I run the program. So you can do this by setting always the same folder name here. In this case, I will just say that I want to use a library file which will be called phenol lib, and it will be placed in the moles folder. So now I'm going to save it, and now I have an input file with the coordinates for my molecule, and I have the PCF file, and now I can convert the PDB file that I created with Gauss View with DLPGEN to create the gen file. And to do that, I will just run DLPGEN -conv, because I just want to convert the file, and then I need to say that what I want to convert is a PDB file. So when I run it, I have now the phenol, the PDB file which was read, okay, and the gen file which was created, also okay. So if we go to the moles, now I should have the gen file here, and we can just check it. Basically, it has the structure. Basically the initial part of the file is consisted with a XYZ file structure, but it doesn't have a title, and it also has these indexes before the atom name, which I will just show you why they are here. And then we also have a PDB file structure in the bottom, where the atom names was changed with an index regarding the position of each atom. This will allow me to know exactly what atom I have in the molecule. And to do this, I'm going to open this file using Mercury. You can use any other program if you want. I like Mercury because it's kind of user-friendly regarding this issue. So I just opened the phenol.gen file, as you see here, and if I go to show labels, now I know that this carbon is in first position, second, third, fourth, fifth, and so on. So now it's easy to come here and say exactly, or to know exactly which atom I need to rename. So to do that, I'm going to open the Emacs, the phenol.gen file, and now I'm going to change the atom names with the names that will then be used in the library file to ID each atom in my molecule. And first atom is this one. I'm going to label it as CAP because it will be different from all the aromatic carbons in the rest of my molecule. So all remaining carbon atoms will be Ca for aromatic. By the way, I'm using the nomenclature in OPLS, and I'm going to prepare all these input files according to the OPLS parameterization. Now I have the hydrogen in the 7th position, which is this one here, so it will be a HA in this case, and the hydrogen of the hydroxyl group is the last one, is 13. Okay, so these two are the hydroxyl group atoms. So all the other ones are HA. Now the oxygen in the 12th position, here it will be the OH, and of course the last hydrogen will be. As you see, it's rather easy by opening the gen file with another program like Mercury, and you will have access to the position of the atoms in a very easy way, and then it's more easy to edit your file with the names that you need. Now we have our gen file prepared, and what we need to do next is to create the library file. And for this I'm going to use do something similar as for the PCF file. So first of all, I'm going to create the library file, phenol.lib. And now I'm going to the manual and I'm going to look for the library file information. And so here it is. We have the data here. Now we have an example of the file. So the first thing I'm going to do is just copy the initial instructions. Okay, so I'm going to copy these files. Oh, sorry, these initial lines. So units will be kilojoules per mole. Then I want to start with the atom section. Now I want to start by saying all, or the first thing I need to say it's all atom types I have. So I'll start with CAP. Okay, well I'll start with Ca for these aromatic carbons in my molecule, and the code name which will be used to ID the bonds, angles, and dihedrals potentials will be Ca. Regarding the mass is 12.011. I'm just going to separate this a little bit. Now the charge for an aromatic carbon according to OPLS is 0.115 minus 0.115. The epsilon is 0.2931 and the sigma is 3.55. The next atom that I want to add here is the CAP atom, which will be recognized for the bonds, angles, and dihedrals as a normal aromatic carbon. And so for this I will use the same name for an aromatic carbon. This will allows me to reduce the number of parameters that I have to introduce in this file. So next thing that I need to do is just to add the mass and charge information. In this case, CAP has a charge of 150, and now I want to record the aromatic hydrogens. It's 1.008. The mass, the charge is plus. This is 0.115. 5. The epsilon for an aromatic carbon is 256, and the sigma is 2.42. Next, I want the OH, will be also recognized as OH. It's 15.999. The charge of an OH is minus 0.585. The epsilon is 0.7118, and the sigma is 3.07. Okay, and the last atom remaining is the HO. The mass is the same as for the other hydrogens. The charge is plus 0.435, and in the case of the epsilons it's 0. Okay, and now all the atoms are set, and we need to finish this section with N atoms. Okay, so I'm just going to record it. Now we need to set the bond types. So it's here. So we need to start these. The only information you need to add or to include in this file is the bond information. These K and B0 will be ignored by DLPGEN. These are optional. This is just for me for us to know exactly what is in each column. So next thing we need to do is to set the different types of bonds. So we'll have CAs interacted with another CAs. The constant for this is 3927, and the equilibrium distance is 1.4. Then we will have CAs, HAs, 3073 and 1.08 for equilibrium distance. CA OH 3768, equilibrium distance 1.364, and finally the HOOH with a constant of 4630, 0.945 for equilibrium distance. And now we need to end the section with N bonds and repeat the same procedure for the angles. Okay. So in the case of angles, we'll have to define the CA. The constant is 527, equilibrium distance 120, HA, constant 293, once again 120. Now CA OH with 586, 120 as an equilibrium angle, and OH with an angle of 293, sorry, with a bond with the angle constant of 293 and 113 as equilibrium distance. And I finish with the end section and instructions here. Now to finish, we are almost done. Now it's dihedrals. So let's start by setting data for this. So regarding the dihedrals, we will have the dihedrals between CA, CA, and in the case of dihedrals involving two aromatic carbons, only V2 or the second Fourier constant is needed. In this case, it's 30.3545. I'm going to do some more space here. Okay. Now this V3 and V4 is 0, and in this case, as I told you before, we can use two different types of dihedral functions, and for a Fourier series, the code is 1. That's what I'm going to use here. As I said before, all dihedrals involving two aromatic carbons have the same V2 constant. In some programs, it's possible to use a wildcard. This is not the case of DLPGEN. So I really need to define every single possible configuration for this. So I'm just changing the different possible possibilities. Now I need CaCaOH, HaOH, and on purpose I will miss one dihedral so that you can see the effect in the program. And finally, I will also do something, which is I will put a duplicate here in the bonds. This is just for you to see what happens when you do this sort of small mistakes. And finally, we have the improper section, and for this we can, I'm going to, impropers. Okay. In this case, you can only use a Fourier series, so there is no code to introduce, and then I can include the potential for this. It's just also a V3 function, and I should have some improper dihedrals that will be in this form. And now to finish, the improper dihedral for an aromatic carbon is 9.205. So at this point, I already have all my input files finished. And now what I'm going to do is I'm just going to open a new window. And I'm going to get in to the folder where I'm working on. Sorry, letters. And now what I'm going to do is to run my program in order for you to see what is going on, what's going to happen. So I'm going to use DLPGEN. In this case, I already have a gen file, so I don't need to convert anything. The library file is already present, so to run the program, I just need to run it like this. So if I run it, I will have a message saying that, first of all, in the force field, I have a duplicate entry for the bond in the hydroxyl group. As I told you before, I on purpose duplicated this. So this means that if you repeat any bond, angle, dihedral, improper, atom. If you set it twice to avoid problems of consistency, you will receive a warning saying that you have a duplicate here. So you can eliminate it. Now I just correct this error. I will run the program again, and I receive now an error saying that I have missing a dihedral, which is this one here. Okay, so I just copy it and I'm going to insert it here. Remember that in this case, the program DLPGEN is giving me the atom names that are in the gen file, not the atom names that are coded in the angles, bonds, and dihedrals. So this means that I have a CAP here, but because in the atom section I define all CAP atoms as CA, this means that I have to correct this in this section here. And now I need to introduce the potential. In this case, for the torsion of this bond around this carbon-oxygen bond, the potential is 0.0, 7.0422, 0.001. So now, if I run the program, it should be okay. And what it's saying now is that I have missing an improper dihedral for this bond. So what I need to do is just adding this one here. This will be CA. Okay, this will be the potential that is missing. Once again, I change the CAP into CA, and because you can define two improper dihedrals for these, I will also have to set this one. Now if I run, there is still one more missing. I also want this one, of course, and I just need to change this. And now it has run and create all the necessary information. There is something wrong here. I must have a mistake in my charges because it's telling me that the total charge in my system is minus 60 instead of 0. And basically what I have is minus 0.3 charge in my for each phenol molecule. So I just need to correct this. Let me see what's wrong. So the aromatic carbon is minus 0.115. The CAP is plus, sorry, problem is here. So this is plus, the carbon is plus, not minus. So that was the mistake. And now if I run it again, no more warnings. So now it's finished. So when I'm preparing a molecule from scratch, I normally what I try to do is I'm continuously running DLPGEN and correcting all the warnings she is giving me. So this is easier to do than guessing what are the angles, bonds, and the other potentials that are missing in my library file. So you can go and edit as the program requested to you. Regarding the input files now, if we go to see the field file, as I told you before, by default DLPGEN will create input files for DLPOLY. So if I type more field, you'll see that we have here the information about my molecule. It has 200 molecules in my simulation box. I have the bonds constraints, so all hydrogen carbon bonds and oxygen hydrogen bonds were converted into constraints. We have the Engels potentials, the dihedrals, and the van der Waals potentials here. Now, if we open the config file, so if I just say more config, we have the config file in the initial structure for DLPOLY, and if you want to take a look in the file, the program also created a config.pdb, which I will open using VMD. And here it is. And so you can see the simulation box that it was prepared by DLPGEN. As you see here, the program does not try to stack the molecules in a very efficient way. So basically what the program creates is an expanded simulation box, which must be calibrated before start doing production runs. Another option to do this is to use PACKMOL during compilation. And to do that, you can go to DLPGEN. We say that for example that we want to create a simulation box with a density of 0.8, let's say, and then in this case I will also ask for the verbose mode, so that all information about the calculations will be printed, and I will record this information in a log file. So the program is run. Let's see what he has just done. So if we look to the output of the program, we have the information that was retrieved from the DLPGEN, from the PCF file. Then it starts reading the gen file. First thing it does is to compute all possible interactions between the molecules, the distance that it was obtained, and if according to the criteria in DLPGEN, if it has considered this, the interaction between these two atoms is a bond. It does this for everything. In the end, it just say that it found 13 atoms and 13 bonds, and it gives me a list of the bonds that were found by the program. Next, it starts producing the connectivity in the molecule, so the number of constraints, rigid units, which in this case were not set, bonds, angles, dihedrals, and impropers that were found. It also tells me that the charge, as it should be, it's 0. It computes the van der Waals interactions, and it writes the field file. Then basically it starts preparing the calculation for PACKMOL. It gets the molar mass of my molecule. I know the target density, and it sets that the box should be a square with 33.93 angstrom sides. And then it calls for PACKMOL, and it runs. And in the end, it converts the config file .pdb, which was created by PACKMOL, into a normal config file. And now, if we open again with VMD the config file, we will see that all the molecules were randomly distributed inside a square box. Normally, people tend to pre-calibrate or to minimize the interactions when they prepare the simulation box using PACKMOL. With my experience is that with the conditions that are now by default introduced in PACKMOL, you can start immediately calibrating the simulation box without need of an initial minimization. So to finish, I would just like to show you that how can you prepare the input files for GROMACS, and in this case you just need to say that you want the DLPGEN to create a GMX input file. It runs as before, and then basically it creates, in this case, a topology file, a molecular ITP file. In the future versions, you will only going to get a topology file containing all the information, and of course the config.pdb file that is required to run GROM with GROMACS. And if you see, if we go to the topology, you can look at it. So it has information about the system. So phenol 200 molecules, and we can go to molecular ITP, and you have all the information here regarding the force field for a molecule. Okay, with this I end this presentation, and in the next tutorial I will try to show you how you can use the auxiliary data in my web page. So all these files here to produce or to create simulation boxes for ionic liquids. So see you in the next tutorial.